Gasoline is one of the most consumed fuels on the planet. Around 800 million vehicles burn through more than 7 billion liters, nearly 2 billion gallons of fuel every single day. But before it ever reaches a gas station pump, that flammable liquid travels through a remarkably long, complex, and potentially dangerous manufacturing process. Have you ever wondered how gasoline is actually made and how the very same machines that produce it can, under the wrong conditions, become ticking time bombs? Today, we are tracing that entire journey from the moment crude oil is pulled out of the ground to the 5 specific failure points inside a refinery that have, again and again, ended in fire, shrapnel, and tragedy. Stay with me until the end, because what you are about to discover will change the way you think every time you stop to fill up. Gasoline begins as crude oil, a thick, dark liquid formed over millions of years from the compressed remains of ancient marine organisms, buried deep beneath layers of rock. Long before a single drop reaches a refinery, geologists spend months, sometimes years, studying sediment layers and rock formations, searching for the faint signatures that suggest hydrocarbons might be trapped below. They use seismic surveying, sending powerful sound waves deep into the earth and reading the echoes that bounce back, essentially giving the planet a full-body scan. When the data looks promising, an exploratory well is drilled, and even then, striking oil is never guaranteed. When a well does strike oil, the crude begins an extraordinary trip. Steel pipes are lowered thousands of feet underground, cutting through granite, shale, and sandstone that has sat undisturbed for hundreds of millions of years. Drilling mud circulates constantly through the well, cooling the drill bit, carrying rock fragments to the surface, and maintaining enough pressure to prevent a blowout, the sudden, violent release of oil and gas that can trigger explosions and environmental disasters within seconds. Once the target depth is reached and testing confirms the presence of oil, production begins. In the early stages, natural underground pressure pushes the crude to the surface on its own. Later, pump jacks, those rocking metal structures dotting oil fields from Texas to the Middle East, take over, drawing crude up like a syringe, pulling liquid from deep below. From there, pipelines carry the raw oil to separation facilities that strip out associated gases, including carbon dioxide, hydrogen sulfide, and natural gas. What remains is crude oil, ready for its final and most transformative destination, the refinery. And it is here, inside these sprawling industrial complexes, some covering areas larger than entire towns, that gasoline is born. And where, if something goes wrong, it can also become a weapon of destruction. Modern refineries are staggering feats of engineering. Some cover several square miles, threaded with thousands of miles of pipework, capable of processing over 600,000 barrels of crude oil every single day. Before refining even begins, specialized equipment removes hydrogen sulfide from the crude, converting it into elemental sulfur that gets sold to farms as fertilizer. Nothing is wasted and everything is interconnected, which is exactly why a single malfunction in one part of a refinery can cascade into catastrophe across the entire facility. At the center of it all stands the distillation tower, often called the heart of the refinery. Crude oil is superheated to temperatures above 700 degrees Fahrenheit and pumped into the base of this towering column as vapor. As the vapor rises, it cools and different hydrocarbon molecules condense at different heights, separating naturally like layers forming inside a glass. The heaviest compounds, destined to become asphalt and heavy fuel oil, settle at the bottom. Diesel condenses a bit higher, followed by jet fuel and kerosene, and near the very top, where temperatures are coolest, the lightest molecules condense into gasoline. From a single barrel of crude, refineries typically extract around 19 gallons of gasoline, 10 gallons of diesel, and about 5.5 gallons of jet fuel, along with plastics, lubricants, and dozens of other everyday products most people never trace back to their origin. But here is the part few people ever think about. This distillation tower, the very machine that makes modern transportation possible, is also one of the single most dangerous structures in the entire industrial world. It operates under extreme heat and, in certain refining processes, extreme pressure, holding volatile hydrocarbon vapors just inches away from ignition sources. If pressure inside the tower rises beyond what the vessel can safely contain, whether from a blocked valve, a control failure, or a sudden temperature spike, the result can be a catastrophic vessel rupture, hurling metal fragments and igniting a fireball that can be seen for miles. This is the first of the 5 ways a refinery can explode, and it has happened before, most famously in Texas City in the year 2005, when a distillation-related overfill and pressure release ignited a vapor cloud, killing 15 workers and injuring more than 180 others in seconds. The second danger lurks in a process many people have never heard of: hydroprocessing. To meet modern fuel standards, refineries push crude oil fractions through units that use hydrogen gas under intense pressure and heat to remove sulfur and improve fuel quality. Hydrogen is an extraordinarily reactive gas. It is lighter than air, nearly invisible when it burns, and capable of leaking through seals and joints that would contain heavier gases without issue. When a hydroprocessing unit develops even a small leak, hydrogen can escape and ignite almost instantly, sometimes without warning, because the flame itself is difficult to see in daylight. Refineries invest enormous resources in gas detection sensors, specifically because a hydrogen fire can spread from a pinhole leak to a full structural fire in under a minute. The third way a refinery can explode ties directly back to something we mentioned earlier: the loading and transport stage. Once gasoline passes its octane testing and clears quality control, it flows through underground pipelines to storage tanks and then into tanker trucks bound for gas stations across the country. This stage, oddly enough, is one of the riskier parts of the entire chain. As gasoline flows into a tanker truck, friction inside the pipes and hoses generates static electricity, and the metal body of the truck can accumulate a charge strong enough to produce a spark. Gasoline vapor is remarkably easy to ignite. A single static discharge near an open hatch or a poorly grounded connection can set off an explosion in seconds. This is why every tanker truck is fitted with grounding cables designed to safely discharge static buildup, along with overflow sensors that cut fuel flow the instant a tank reaches capacity, and vapor recovery systems that capture escaping fumes before they have a chance to ignite. The fourth danger sits inside the refinery's furnaces and boilers, the unglamorous workhorses that provide the intense heat needed for distillation and other chemical processes. These furnaces burn continuously, sometimes for years without a full shutdown, and the metal tubes carrying superheated crude oil or hydrocarbon vapor through the flames are under constant thermal stress. Over time, corrosion, metal fatigue, or a buildup of carbon deposits inside these tubes can weaken their walls. If a tube ruptures while still inside an active furnace, the escaping hydrocarbon vapor meets an open flame instantly, with no time for evacuation or containment. This exact failure mode has caused some of the most devastating refinery fires in modern history, including a 2012 explosion at a refinery in Venezuela that killed dozens of people and injured hundreds more, tracing back to a gas leak near operating furnaces. The fifth and final major explosion risk involves storage tanks themselves, the massive cylindrical containers that hold crude oil, gasoline, and other refined products before they are shipped out. These tanks seem simple compared to the chemistry happening inside a distillation tower, but they carry their own unique hazard: vapor space. As liquid fuel sits inside a tank, it naturally evaporates, filling the empty space above the liquid with flammable vapor. If a tank is overfilled, if a vent malfunctions, or if lightning strikes a poorly grounded tank during a storm, that vapor space can ignite instantly, sometimes triggering what engineers grimly call a boilover, where burning fuel violently erupts out of the tank in a wave of fire. This is precisely what happened during the Buncefield disaster in England in the year 2005, when a storage tank was overfilled, releasing a massive vapor cloud that ignited into one of the largest peacetime fires ever recorded in Europe. What makes all 5 of these risks so persistent is not carelessness, but the sheer scale and complexity of the systems involved. A single modern refinery might contain thousands of valves, hundreds of miles of pipe, dozens of furnaces, and multiple massive storage tanks, all operating simultaneously around the clock, processing a substance that is inherently unstable the moment it becomes vapor. Engineers build in layers of protection: pressure relief valves, automatic shutoff systems, gas detectors, fireproof coatings, and redundant safety controls designed to catch a failure before it becomes a disaster. Most days, these systems work exactly as intended, and gasoline moves quietly and safely from crude oil to your fuel tank without anyone giving it a second thought. But every safety system in a refinery exists because of a lesson learned somewhere else, often at tremendous human cost. The Texas City disaster changed how refineries monitor distillation towers during startup. The Buncefield fire led to stricter regulations on tank overfill protection across the entire industry. Furnace tube failures pushed refineries toward more advanced corrosion monitoring and non-destructive testing technologies that can detect a weakening pipe wall long before it ruptures. In a strange way, every gallon of gasoline that reaches a pump today is safer because of the disasters that came before it. Once gasoline clears every stage of production, from distillation to hydroprocessing to storage, it still has to pass one final test before it is allowed to leave the refinery. Every batch is run through combustion engines to verify its octane rating, the number displayed at every fuel pump. Octane measures how resistant a fuel is to knocking, a phenomenon where gasoline ignites too early inside an engine cylinder, causing a sharp, damaging noise and reduced performance. If a batch fails to meet the required standard, it is sent back for adjustment. Only after passing this test is the gasoline cleared for distribution, pumped through pipelines to loading terminals, and eventually loaded onto tanker trucks headed for gas stations. Around 1 million gallons of gasoline leave refineries across the country every single day on tanker trucks, each one navigating highways loaded with a cargo that is simultaneously essential to daily life and inherently hazardous if mishandled. When a truck finally arrives at a gas station, its hoses connect to underground storage tank inlets, valves open, and gravity does the rest, sending fuel quietly down into the tanks beneath the pavement. By the time you pull up, insert your card, and squeeze the handle, that fuel has already survived a journey most people could never imagine: crushing underground pressure, temperatures above 700 degrees Fahrenheit, volatile chemical processes, and 5 distinct points where a single failure could have ended in disaster. It is easy to take gasoline for granted. It sits quietly in an underground tank waiting for the next car to pull up, looking as ordinary as water. But behind that simplicity lies one of the most intricate and carefully monitored industrial processes on Earth, a system built specifically to tame one of the most energy-dense, flammable substances humans have ever learned to harness. Refineries do not just make fuel, they manage risk on a massive scale every hour of every day, balancing efficiency against the ever-present possibility that one small failure, a stuck valve, a corroded pipe, a static spark, could turn a routine process into a headline. The next time you stand at a gas station watching the numbers climb on the pump display, it is worth remembering just how far that fuel has traveled and how many engineers, sensors, and safety systems work together silently to make sure it reached you the way it was supposed to, contained, stable, and ready to power your journey rather than end it. If you enjoyed this episode, drop a like, share it with your friends, and leave a comment telling us where you are watching from. Subscribe and turn on notifications so you never miss a new upload. Thanks for watching. We will see you in the next one.